know that water is one of our most precious resources? But with pollution and climate change threatening its purity, how can we ensure its sustainability for future generations? Well, the answer lies in biochemistry.
Enzymes speed up chemical reactions. They work by binding to one or more specific molecules called reactants or substrates. Binding occurs at a special region on the enzyme called the active site. Once the substrate bind to the active site, they form what's called an enzyme-substrate complex. As the enzyme and substrate begins to react, some of the chemical bond in the substrate begin to weaken, causing them to link together. Eventually, the chemical reaction at the active site lead to the formation of different molecule called the product. Once the reaction has occurred, the product is released from the active site. The enzymes return to its original state and is free to react again with another set of substrates.
One of the most powerful applications of biochemistry is pollution control. Specialized enzymes and bacteria can naturally break down harmful substances, reducing industrial waste and agricultural runoff. When a river is polluted, whether from industrial waste, agricultural runoff, or sewage, biochemists can use enzyme-based bioremediation to break down harmful contaminants naturally. Here's how the process works. 1. Identifying pollutants. First, analyze the water to determine the type and concentration of pollutants. 2. Selecting and applying enzymes. Specific enzymes are chosen based on the pollutant's presence.
Enzyme action. Lock and key hypothesis. This is the simplest model to represent how an enzyme works. The substrate simply fits into the active site to form a reaction intermediate. Just like the key fits in its specific lock, the shape isn't changed here. Rather, the structure of the substrate absolutely complements the structure of the enzyme, like puzzle pieces. Induced fit hypothesis. In this model, the enzyme, upon binding of substrate, changes shape. The matching between an enzyme's active site and the substrate isn't just like two puzzle pieces fitting together. Rather, the enzyme changes shape and binds to its substrate even more tightly. This fine-tuning of the enzyme to fit the substrate is called induced fit.
3. Enzyme activation and breakdown of pollutants. Once introduced, the enzymes begin breaking down pollutants at a molecular level. 4. Monitoring and reassessment. Continuously monitor water quality through biosensors and chemical assays to track how well the enzymes are performing. 5. Restoring the ecosystem. Over time, the enzymes help restore natural balance by reducing toxin levels, improving oxygen content, and allowing aquatic life to thrive again.
By analyzing biochemical markers across various water bodies, scientists can identify long-term trends in water quality and predict potential contamination threats.
Government agencies and organizations use biochemical data to create policies that ensure clean water standards are met. This information helps drive environmental conservation efforts worldwide.
Oxygen given sa tulo ka sample and it is 8.95, which did not meet the standards of DENR malfunction and failure.
Modern biochemistry-driven technologies such as biosensors and DNA-based diagnostics are revolutionizing water management. These tools help detect pollution sources and assess water quality more accurately than ever before. Through science and innovation, biochemistry continues to shape the future of water quality management. Let's work together for a healthier planet, one drop at a time.